So far, we've looked at statistical tests for hypotheses about a single group at a time. We looked at a test of a mean to determine whether the population mean for a given group is equal to some special value, for example, to determine whether the oxygen content in the lake is the same as it was 10 years ago. And we looked at the test of a proportion to determine whether the population proportion for a given group is equal to some special value, for example, to determine whether the astrologers were doing better than guessing the personality profiles. But sometimes we're interested not in the particular value of a mean or a proportion, but whether the means or proportions for two groups are the same or different. For example, we might want to know whether men and women have the same average salary, or whether one candidate has more votes than another candidate. In this session, we'll cover three types of differences: differences between matched pairs, differences in the means of independent groups, and differences in the proportions of independent groups. First, the test of paired differences. A researcher was studying the effects of talking on a cell phone while driving. The researcher had a group of students using a driving simulator. Each student went through the driving simulator twice, once while they were talking on a cell phone about a political issue, and once without using a cell phone. In the simulation, a light changed unexpectedly from green to red, and the researcher measured how long the drivers took to apply the brake. At the end of the study, the researcher has two lists of measurements: one list while drivers were talking on the cell phone, and one list without talking on a cell phone. But these two lists are related. Each number in one list can be paired with a number on the other list. How do we pair them up? According to which driver the measurements came from. Recall that each driver entered the simulator twice, once with and once without a cell phone. And the reaction times for a given driver are likely to be related. A driver with a generally fast reaction time is likely to be relatively fast whether or not they're talking on the cell phone. And a driver with a generally slow reaction time is likely to be relatively slow whether or not they're talking on the cell phone. In this study, the researcher could have divided the group of students up randomly to conduct an experiment in which half of the students talked on the cell phone while driving in the simulator, and the other half focused entirely on their driving. It certainly would have taken less time for each subject, since they would only have to go through the simulation once. Is there some advantage to measuring each subject twice? It turns out there is. Sometimes the variability between subjects is greater than the differences between the groups. For example, the variability in reaction time, how fast or slow someone is at pressing of the brake, may be quite large relative to the difference in the average reaction time while talking or not talking on a cell phone. Perhaps the data looks something like this. Notice how spread out all of the observations are. Can you tell whether the average for one group is higher or lower than the average from the other? It's kind of difficult. The variability in the data make it difficult to say. But if you connect the pairs of observations that come from the same driver, suddenly it becomes quite clear that in most cases, drivers have slower reaction times when they're talking on their cell phones. Studies that make use of paired data like this usually have greater statistical power than studies that rely on independent groups, because you can use the pairs to factor out much of the variability between subjects in order to focus more clearly on the differences you're interested in this case, the effect of using a cell phone on braking reaction time. Once you know how to conduct a test of a mean, conducting a test of paired differences is a piece of cake. You simply compute the difference in each pair, and then you conduct a test of a mean on the differences instead of the original data. Let's take a look at how this works for our cell phone example. First, we have our assumptions. The first and most important assumption is that we have two different measurements for each subject, or other paired observations. Then we have to follow the rest of the assumptions for the test of a mean. So we have to have interval ratio measurement, we have to have randomization, and our population either has to be approximately normal or we have to have a large sample size, at least 30. Next are hypotheses. The null hypothesis is that the difference between the two means is zero. That is to say, the difference in the reaction time for drivers who use a cell phone and when they're not using a cell phone is zero. There's no difference. The alternative hypothesis, then, is that there is a difference between the two groups of measurements. We want to see whether there's any difference between the two measurements for each subject on average. In this case, we're looking to see if talking on a cell phone makes a difference on reaction time. If talking on a cell phone makes no difference, then the difference in the average reaction time with and without a cell phone will be zero. Next, we have our test statistic. We take the difference in the sample means of the two sets of measurements, x2 and x1, and divide by the standard error. Or another way of putting this is we take the average of the differences for each pair and divide by the standard error. Remember that the standard error for a mean is the standard deviation divided by the square root of n. Here, the standard deviation that we're going to use is the standard deviation of the paired differences, not the original measurements. This test statistic has a t-distribution, and the number of degrees of freedom is one less than the number of pairs or the number of subjects, just like in our test of a mean. So here are the data for our cell phone example. In this case, the mean reaction time when students were using a cell phone was 585.2 milliseconds, and the mean reaction time when students weren't using a cell phone was 534.6 milliseconds. In this sample, they were 50.6 milliseconds faster without a cell phone. But these results could be a little different in another study. We want to know whether this 50.6 millisecond difference gives us statistical evidence that the average reaction time without a cell phone is smaller than the average reaction time with a cell phone. Which standard deviation are we going to use for our test statistic? We want the standard deviation of the differences in the paired measurements. In this case, it's 52.49. Our test statistic is t equals the average difference divided by the standard error. So that's 50.63 milliseconds divided by the standard error, which is 52.49 milliseconds divided by the square root of our sample size, which is 32. That gives us a test statistic of 5.46. We're going to compare this with a t-distribution with 31 degrees of freedom. We have 32 in our sample size, we take off 1, and that's the number of degrees of freedom we have. The two-sided 0.05 critical value for this distribution is 2.04, so we could compare our test statistic 5.46 with the critical value 2.04, and we see that the test statistic is larger, so we know that our results are statistically significant. Or we could compute the exact p-value for our test statistic. In this case, it's less than 0.001. That means that if there really were no difference in drivers' reaction times with and without a cell phone, in a very small number of studies, less than 0.1%, we would see at least a 50 millisecond difference in cell phone and non-cell phone reaction times, even though really there were no difference. So we draw our conclusion that using a cell phone while driving seems to cause slower reactions. The test of paired differences is useful if you have two measurements on each subject. But there are many times in which you're interested in the difference between two different groups, not two measurements on the same group. For example, researchers were investigating how quickly teenagers form addictions to nicotine after they start experimenting with smoking. They obtained a random sample of 332 Massachusetts 7th graders who had used tobacco before, and gave them the Hooked on Nicotine checklist. This was a measure of addiction. The researchers wanted to know whether males and females who had tried smoking had the same level of nicotine addiction on average. Here we have two separate groups, the male 7th graders and the female 7th graders. We have the same measurement for both groups, that's the nicotine addiction, not two different measurements for one group. And these groups are not paired. To determine whether the two groups have the same mean, we can conduct a test of two independent means. First, the assumptions. The first assumption is that we have two independent groups. The independent groups assumption is very important here. These two groups need to be unrelated to one another. Dependent groups could be something like a parent and a child who are related because they live in the same family, or siblings in the same family, or a teacher and a student. Any way in which these subjects could be grouped together because of some relationship that they have. In this case, the males and the female students don't really have any particular relationship with one another, so we have independent groups. The rest of our assumptions have to follow the same assumptions as the test of a mean. So we have to, as before, have interval ratio measurement, randomization, and our population has to be approximately normal, or we have to have a large sample size, at least 30. Next are hypotheses. In this case, we have two population means, one population mean for each group. And our null hypothesis is going to be that the means of the two groups are equal. mu1 equals mu2. So the alternative hypothesis is that mu1 does not equal mu2. On to our test statistic. Here we can take the difference in the sample means for the two groups and divide by the standard error. Now the standard error here is going to be a little different than before because we have a standard deviation for group 1 and a standard deviation for group 2. We need to combine them. So we'll take the square of each of these standard deviations and divide it by the sample size. Then we'll add those together and take the square root. So we take the standard deviation for group 1 and we square it and then divide by the sample size for group 1. And we add that to the square of the standard deviation for group 2 divided by the sample size for group 2. And then we'll take the square root. And that will give us this total standard error that we'll use for this test statistic. The sampling distribution for this test statistic is approximately a t-distribution. It's not exactly, but it's pretty close. And there are a couple of different ways to estimate the degrees of freedom that should be used for this test statistic. One simple method that we're going to use is to simply take one less than the sample size of the smaller group. So we have two sample sizes, one for each group. We'll find the smaller group and we'll use one less than that as the degrees of freedom for our test statistic when comparing to a t-distribution. So here are the data for our nicotine addiction example. We see that we had 150 females and 182 males, and the mean addiction score for the females in this sample was 2.8, and the mean addiction score for the males in the sample was 1.6. So our standard error is computed from the standard deviations for each of the two groups. So we'll take group 1 standard deviation 3.6 and square it and divide by the sample size for group 1, that's 150. And we take group 2 standard deviation 2.9 and square that and divide by the sample size for group 2, which is 182. And we'll simplify that and take the square root, and that gives us a standard error of 0.364. So when we compute our test statistic, we'll take the two sample means, 2.8 and 1.6, and we'll take the difference. And we'll divide by the standard error, 0.364. That gives us a test statistic of 3.3. How many degrees of freedom do we want to use? Well, we need to find the group with a smaller sample size. That's females in this case. So they were 150 female students. We'll take one less than that, so we have 149 degrees of freedom. When we compute the two-sided p-value, we get 0.001. That's less than 0.05, so we can conclude that male and female students who tried tobacco developed different levels of addiction to nicotine. Finally, we can also look at the difference between two independent groups when we've measured a nominal variable and are interested in the population proportion instead of the population mean. For example, aspirin may have health benefits beyond just relieving headaches. One study investigated whether aspirin could reduce the risk of heart attacks. In this experiment, participants were randomly assigned either to take an aspirin or a placebo every day for the duration of the study. Researchers recorded how many participants in each group had a heart attack. Here, the measurement, heart attack or no heart attack, is nominal, and we're interested in whether the population proportion of people who had heart attacks is the same for people who took aspirin or who took the placebo. So first, let's look at our assumptions. Just as before, our first and most important assumption is that we have two independent groups. So the subjects in the aspirin group can't be related to the subjects in the placebo group. All of the other assumptions are the same as for the test of proportion. So we need to have nominal measurement, we need to have randomization as always, and we need to have a large enough sample, at least 15 expected successes and 15 expected failures for each group. So our hypotheses are much like the hypotheses for the test of two means, except here we're talking about proportions. So our null hypothesis is that the proportion for group 1 is the same as proportion of group 2 in group 2. And our alternative hypothesis is that the two proportions are different. So let's take a look at our test statistic. As before, we're going to take the difference between the two estimated proportions for group 1 and group 2 and divide by a standard error. Now, you may recall that our standard error for a proportion is the square root of p, 1 minus p, divided by n. What p are we going to use here for the standard error? When we conducted the test of a proportion with just one group, we were comparing the sample p to some special proportion from the null hypothesis, like 50% if we wanted to know about the majority. Here, our null hypothesis doesn't have any particular value for the proportion. We just want to know whether the two proportions are the same or different, whatever they may be. If the null hypothesis really is true, then the proportions are the same. So we can pool all of our results from the two groups to find a pooled or overall estimate, p hat, for the common proportion. Then we can compute our standard error based on this common or pooled proportion, the square root of p hat times 1 minus p hat, times, and then we need to combine the two sample sizes. And the way we do that is we take 1 over the sample size for group 1, and we add it to 1 over the sample size for group 2. And that will give us our standard error for the test of two proportions. As with the test of a proportion with one group, our test statistic for this test of two proportions also has a standard normal sampling distribution. So we'll compare our test statistic to the standard normal distribution. So here are the results for the aspirin heart attack study. We see that there were about 22,000 participants total, and in the placebo group 189 had a heart attack, and in the aspirin group 104 had a heart attack. So we can compute the sample proportion for both the placebo and the aspirin group. The placebo group proportion is 189 divided by 11,034. That gives us a proportion of 0.0171. And the sample proportion for the aspirin group is 104 divided by 11,037, and that gives us a sample proportion for group 2 of 0.0094. The pooled estimate is going to be based on the total row that combines the two groups. So our pooled proportion is 293 divided by 22,071. Then we'll use that pooled proportion in our standard error computation. So we'll take 0.0133 times 1 minus 0.0133, and we'll multiply by that term that has to do with the sample size. So we'll take 1 over our group 1 sample size, 11,034, plus 1 over our group 2 sample size, 11,037. When we simplify all of that and take the square root, we get a standard error of 0.0016. So for our test statistic, we'll take the difference in the two sample proportions for the two different groups, 0.0171 minus 0.0094, and divide by our standard error, 0.0016. This gives us a test statistic of 5.14. We compare that to a standard normal distribution, and we get a very, very small p-value, less than 0.001. So our conclusion is that aspirin is connected with a lower risk of heart attack.